This is part 2 of Chapter 11 Practice Problems, and this will be the last video of General Chemistry 1. We'll go ahead and get started with example 11.8, and it reads, Carbon dioxide is effective in fire extinguishers partly because its density is greater than that of air. So carbon dioxide can smother the flames by depriving them of oxygen. It gives the density of air, which has a density of around 1.2 grams per liter. That's at room temperature in normal sea level atmosphere, which is 1 atm. We're asked to calculate the density of carbon dioxide at room temperature, which is 25 degrees Celsius. And of course, we want to compare the density to air, so we're also going to look at the same pressure at 1 atmosphere. Our strategy would be to use this formula that's given for density. This is going to use pressure. This cursive uppercase M is going to represent our molecular weight of the gas we're looking at. R is our gas constant, and we want to make sure that we use the one that has the correct units so that all the units will play well with each other and cancel. T is temperature in kelvins. The gas constant that we'll need with these units is going to be 0.08206. This has units of liters, atmospheres, Kelvin, and mole. And again, we're reminded to express the temperature in kelvins. The molar mass of carbon dioxide, which we've calculated before in this semester, is 44.01. And just to remind you, you'd look up carbon, you'd look up 2 oxygens, add all 3 together, all 3 of the numbers. 44.01. We just plug and chug this, meaning we just put it in where the variable is and pop it in our calculator. Pressure is 1. Our molar mass is 44.01. Our gas constant is written in, and our temperature in Kelvin. You can see the atmospheres are crossed out because they cancel. The Kelvin is canceled out, as well as the moles. This will leave us grams, and it'll also leave us liters, which is the units that density is usually in for gases. Again, liquids are usually grams per milliliter. Gases are a lot of times expressed in grams per liter. Why do they have different units? Well, it gives us easier numbers to work with. If we had this in milliliters, and you're going to have a difference of 1,000. Same thing with density of a liquid. If we had it in liters instead of milliliters, it'd be a difference of 1,000. The number's not as friendly, meaning that it's going to be a big number or a really small number that's a decimal. But using these units, you can see we just get nice numbers that we can wrap our mind around. When we plug all this in, we should get 1.8. That does match the statement that the density is more than air, so it's 1.8 versus 1.2. If something is more dense than, if 2 substances are being compared and they're in the same environment, whichever is the more dense is going to be the lower of the phases. If we think about this, our calculated density is greater than that of air. And then, although it may seem tedious, it's a good idea to write units for each and every entry in a problem such as this, because we want to make sure that we have everything in the right units. If we use the incorrect gas constant, our units won't cancel. If we don't convert temperature into kelvins, the units wouldn't cancel either. Moving on to example 11.9. This reads, a sample of 3.5 moles of ammonia gas occupies 5.2 liters at 47 degrees Celsius. Calculate the pressure of the gas in atmospheres using A, the ideal gas equation, and B, the van der Waals equation. So an ideal gas looks at a gas in a vacuum where we don't have any external influences, and it's like an ideal or perfect situation. Now, in the world, there's not going to really be perfect situations of a gas. The environment will change. So they have these, you can kind of think of them as fudge factors, meaning that it kind of alters our numbers. Let me explain this just very briefly. If we calculate something in an ideal gas equation and compare it to a real experiment, we'll notice that our numbers are slightly different. So then what we can do is look at some common gases, and that's what they did with the experiment. They looked at common gases and then found the differences. They came up with these equations where it has van der Waals as the scientist, and they're going to bump into each other, and they're going to have some external influences, and these numbers are taken into account here, as I'm highlighting, this an squared over v squared, and then nb. Now, let's go through this, and really it's not too difficult, even though it looks a little intimidating. It's again, you just plug in the values and multiply everything and subtract or add when we need to. So of course our strategy here is to use the ideal gas equation, PV equals nRT, and then to also use the van der Waals equation. It's still PV equals nRT, but there's going to be a variation in the pressure. So we're going to have this component added to the pressure, this component subtracted from the volume, and it's still equal to nRT. The number or the amount of the gas, the number of moles or amount, is constant, and it will not be altered, so we don't need a, what I like to say, fudge factor that changes the value slightly. The gas constant is of course a number that doesn't change. And then the temperature, we can usually regulate a temperature, or have it in a case where we measure the temperature with a thermometer and we can perform multiple readings. The two components that really are altered are the pressure and the volume. Alright, so if you're more interested in this, just look up additional information. I won't take any more time discussing it. Let's look at how these numbers are different. So we will look at pressure, and we'll rearrange our PV equals nRT to isolate pressure. And what they've done here is just divided volume on both sides. So it's pressure equals nRT over V. The amount of the gas is given as 3.5 moles, the gas constant, which we can look up, and this is the most common gas constant used. The temperature is converted into Kelvin from Celsius, just adding 273.15. And the volume is also given, 5.20 liters. We multiply these numbers up top and divide by the denominator. We get 17.7 atmospheres. Now if we look at our correcting factors, we take into account an squared over v squared. That's going to be this written here. We'll need to look up these values in a table. So they have tables with the values of these correction factors, or fudge factors if you will. And for ammonia, A is this value. Here's N, and then our V. Our V is of course just whatever volume is given. We're going to correct the volume in a moment. So we have an squared over v squared, and this comes out to 1.89. And then we can also look at it for the volume. The N is still 3.5. So the only thing that we got from the table is A. And then we'll also get B in this second part. And then we multiply by this factor, and this gives us 0.130 liters. So this would be our correction factor for pressure. This is our correction factor for volume. And that's comparing the ideal gas to the van der Waals. Now, we'll take those values, and then we can substitute them in. So we already calculated what the pressure is from van der Waals, which is 17.7. So we'll take that, add the pressure of the correction factor. We take our volume that's given, subtract the correction factor. And then we can figure out the pressure. And actually the way they've worked this out is a little different than I just explained. So we can solve for the pressure. So solve for the pressure, add the correction factor. They leave this as a variable. You do some algebra here. Just be careful with your algebra. Go ahead and you'll want to subtract when you need to, or divide, and then pull things out. The algebra here can get a little fuzzy, so just practice with it. And then this comes out to 16.2. And then The usual trend, as it's listed here in the think about it, it says, as is often the case, the pressure exerted by the real gas is lower than predicted by the ideal gas equation. And that's just because of external influences. It'll lower the pressure slightly. So we're comparing 16.2 to 17.7. So a real gas is definitely different than what we get for our ideal. If we're doing some very intricate work in an industrial setting where the pressure is extremely important, we could do one of two things. One, we'll put the situation in a vacuum inside a chamber, use the ideal gas. We'll still use the van der Waals and make sure that everything, see how close the numbers are. And so they have to be really accurate with it, or you can have some pretty dangerous situations happen. Alright, so let's take a look at 1111. I actually took out 1110 because I noticed an error in the question. So I did a video, or had it in the video, but then ultimately needed to omit that one. Alright, so this one reads, a 1 liter vessel contains 0.215 moles of nitrogen gas and 0.0118 moles of hydrogen gas at 25.5 degrees Celsius. Determine the partial pressure of each component and the total pressure in the vessel. And this may seem a little complicated, but it's not too bad. All that you're going to do is use the ideal gas law, calculate the pressure for one molecule, calculate the pressure for the second molecule, and then add them together. This way we'll be able to have information of how much pressure is contributed from each of the different components. And then you can do percents from it and so forth. Alright, so let's take a look at this from the given information for nitrogen. This is PV equals nRT. We've divided both sides by volume so that it will now read pressure equals nRT over V. Plugging in these values, we have the amount, so 0.215, this is for nitrogen again. We have the gas constant. The temperature needs to be in Kelvin, so this temperature in Kelvin. And then our volume is said to be a 1 liter vessel. So the pressure for just the nitrogen, when we calculate this, is 5.27 atmospheres. We could do the same thing for the hydrogen. Notice all of the variables are the same except for the amount. The amount is different. So you put in the amount that's given for the hydrogen. You calculate this pressure, that's 0.289 atmospheres. We add these two values together and you get a total pressure of 5.56 atmospheres. So not too bad. And one thing to remember is the total pressure in the vessel can also be determined by summing the total number of moles in the mixture and then using the ideal gas equation. You can try that as well and convince yourself. So taking the 2 molar values and getting this, and then just doing the calculation once, you should get the same thing. 11.12 is our next problem. In 1999, the Federal Drug Administration approved the use of nitric oxide, NO, to treat and prevent lung disease, which occurs commonly in premature infants. The nitric oxide used in this therapy is supplied to hospitals in the form of a nitrogen-nitric oxide mixture. Calculate the mole fraction of nitric oxide in a 10-liter gas cylinder at room temperature that contains 6.022 moles of nitrogen, in which the total pressure is 14.75 atmospheres. So it's very similar to the last question we looked at, but just looking at it from a different perspective. We'll again use the ideal gas equation, and then just know that part over whole is how we'll get percent. So first thing we want to do is figure out our total number of moles. We have PV equals nRT, and we solve for moles. So we divide both sides by RT, and that's how you get this relationship. The pressure is given, 14.75, so we just put that in. The volume is 10 liters for the gas cylinder, so that's in there as well. Here's our normal gas constant, you're probably familiar with now. Room temperature in Kelvin, just add 273.15. There's our Kelvin temperature. Checking to make sure all of our units cancel. Everything does except for moles. So we're left with 1 over 1 over moles, which puts moles just back in the numerator. This comes out to be 6.029 moles. We're also told that it contains this amount in moles of nitrogen, so we can subtract 6.029 or subtract 6.022 from 6.029. That comes out to be this 0.007 moles of our nitric oxide. Our ratio, and this is just a ratio, it says to calculate the mole fraction. A mole fraction is the value left is less than 1. If we multiply by 100, then it would be a percent. So it's a percent divided by 100 is our fraction. So it's part over whole. We take our 0.007, divide by our whole, and then we get this. This is our mole fraction. If you're ever asked to calculate the percent, then you just multiply by 100. To check your work, we can determine our mole fraction by subtracting from 1. Using each mole fraction in the total pressure, calculate the partial pressure of each component. So you can just backwards calculate to convince yourself that it works. 11.13. Sodium peroxide, which is Na2O2, is used to remove carbon dioxide from and add oxygen to the air supply in spacecrafts. It works by reacting with carbon dioxide in the air to produce sodium carbonate, Na2CO3, and molecular oxygen O2. Here's our balanced equation. 2 Na2O2 solid plus 2 CO2 gas yields 2 Na2CO3 solid and O2 gas. What volume, and specifically in liters, of carbon dioxide at standard temperature and pressure will react with a kilogram of sodium peroxide, Na2O2? The strategy here is to take our given mass of our sodium peroxide, calculate that to moles. We can do that from knowing our just standards and use our balanced equation to determine our stoichiometric amount of carbon dioxide. And then it will ultimately use our ideal gas equation to convert moles of carbon dioxide to liters. So we're combining multiple things here. We take our equation. Luckily, it is already balanced for us. If it was just written out, boy, that would be a lot of work. You'd have to predict the products, balance it, do the stoichiometry, and use the ideal gas law. But, alright, so let's take this and continue on with it. So our molar mass, just straight from the periodic table, 2 sodiums, 2 oxygens, 77.98 grams per mole. We can treat the specified mass of sodium peroxide as an exact number. 1 kilogram is 1,000 grams. So, and it was asked for with a kilogram. So this is our starting point, 1 kilogram. So 1 kilogram, 1,000 grams, those are equivalent. And then we want to cancel out our grams. This gives us our moles of the sodium peroxide. Check our moles of sodium peroxide in our numbers from the balanced equation. We have 2 and 2. Where do those come from? Well, here's our 2 carbon dioxide. Here's our 2 sodium peroxide. Moles of sodium peroxide cancels. This leaves us with our moles of carbon dioxide. So this would be like a stoichiometry problem from previous chapters. We can then use our PV equals nRT, solve for volume. We'd be left with nRT over P, and we get that just by dividing both sides by pressure. So be able to solve for all the variables in our ideal gas law. So our volume of carbon dioxide is going to have the N, which is our moles, our normal gas constant that we've seen every time so far today, the temperature in Kelvin, and this is just normal, what is this? This is 0 degrees. Standard temperature pressure is 0 degrees and 1 atmosphere. Multiply through and divide by 1, we should get 287.4 liters of carbon dioxide. Now you're thinking, oh, that seems kind of big, and it sure enough says the answer seems like an enormous or gigantor value of carbon dioxide. If you check the cancellation of the units, you can see that it does work. So it's just a really big volume. Continuing on into 11.14. An air purification method for enclosed spaces involves the use of quote-unquote scrubbers. These contain aqueous lithium hydroxide, and it reacts with carbon dioxide to produce lithium carbonate in water. Consider the air supply in a submarine with a total volume of 2.5 times 10 to the 5th liters, the pressure of 0.9970 atmospheres, and the temperature, room temperature, 25 degrees Celsius. If the pressure in the submarine drops to 0.9891 atmospheres as the result of carbon dioxide being consumed by an aqueous lithium hydroxide scrubber, how many moles of carbon dioxide are consumed? Now, what we'll use here is just a variation of our ideal gas law. It's still PV equals nRT. We can solve for moles and then pull out our pressure. And what we'll do is we're going to look at the change in moles and the change in pressure. So then that's all this is these delta values. And this is pulled out because it's the change in pressure, and we're not looking at change in volume or gas constant, which is not going to change in the temperature. Okay. So we'll take the change in pressure, 0.9970, and 0.9891. We look at the difference there, and that comes out to this value. Our volume is just one volume, and then our temperature is, we add 273.15 to this. Okay. So then we can plug in our new pressure and the volume that's given, normal gas constant, and then our temperature, calculate everything. Hopefully everything's calculated correctly. This comes out to 81 moles of carbon dioxide consumed. So we want to make sure that our units cancel, and this amount of carbon dioxide corresponds to 162 moles or 3.9 kilograms of lithium hydroxide. You can back calculate to convince yourself that those will work. Okay. So that would be our number of moles that are consumed. Okay. You don't have to use these delta symbols if you don't want to. You can just know and see that, okay, I am looking at a change in pressure, so that's the first thing I want to do, is calculate what my pressure value will be. And then this would be N equals PV over RT, and then just put in that pressure difference if these delta symbols throw you off. Okay. Last example, 11.15, and should be able to do this video definitely less than 30 minutes this time. This reads calcium metal reacts with water to produce hydrogen gas. Here's our formula, and should already be balanced for us, and luckily it's all 1 to 1 to 1 to 1. Calcium solid reacts with liquid water to produce calcium hydroxide, which is aqueous, and hydrogen gas. Determine the mass of hydrogen produced at room temperature 25 degrees Celsius and 0.967 atmospheres when 525 milliliters of the gas is collected over water. And this is in figure 11.23 if you have your textbook. What we're going to do here is use the law of partial pressures, which comes from John Dalton. And this will allow us to determine our partial pressure of hydrogen. We're also going to use the ideal gas equation to determine the moles of hydrogen. And then we can use the molecular weight or molar mass of hydrogen to convert to mass. And again, as always, pay very careful attention to the units. Make sure that they cancel. Make sure you're using the correct gas constant. For our case, we've been using the same gas constant every time. Make sure that the atmospheric pressure is given in the unit of atmospheres, not millimeters mercury or torricellis or bars or any other pounds per square inch and such. And make sure the vapor pressure of water is tabulated in, what is this? The torr. Playing tricks on us. Should be atmospheres. Some car horn beeped outside to just really key that in. Right? Alright, so hopefully you're still listening to the video. A little bit of humor here to keep you focused is good. Alright, so we have our pressure difference. So This is tabulated in torrs, so we need to go from torrs to atmospheres. And you can look up the conversion factor. It's not too bad. Total pressure, 0.967. We're going to subtract our water pressure from that, 0.0313. This comes from, does it give us this? We can look that up. 0.936 atmospheres. So our moles of H2, we're just taking PV equals nRT, divide both sides by RT, and we get this equation. So we have moles equals pressure, volume, gas constant, temperature. Checking to see your units cancels, atmospheres, liters, Kelvin. We're left with 1 over moles, which puts moles in the numerator. 2.01 times 10 to the negative 2 moles. We can use the molecular weight of H2. 2 hydrogens, not just one. It's diatomic. So that instead of 1.008, it's 2.016. We multiply so that moles cancels. And there we go. Sure enough, mass of hydrogen, 0.0405 grams or 40.5 milligrams. Not too bad. And again, as always, make sure your units cancel. Remember, the densities of gases will be relatively low. And the mass of approximately half a liter of hydrogen at or near room temperature and 1 atmosphere is going to be a really small number. Okay. So that wraps up all of our examples for Chapter 11. It also wraps up all of our videos needed for General Chemistry 1. I hope you really enjoyed these videos and that you've been able to watch them over and over and that they have helped you practice and learn the material. It's been my pleasure to make these for you and for your studies. Thank you so much.